phone. We from Group 3. We present about the investigating vehicle speed recovery after crossing road hump. For the group members, we have Nusahana binti Bohanuddin, Koneho, Muhammad Akmal Kebrosmandi, Winnie Wong, and Joel Rona Justin. This is our overview for this presentation. At the first, we have the introduction, methodology and data collection, and we explain more detail about data analysis and discussion, and we have the sum of suggestion, and lastly is conclusion. For this introduction, the assignment we concentrate on understanding how vehicles recover speed after crossing road hump and the implication for traffic management. Road humps or speed bumps serve as critical tools for moderating vehicle speed in specific areas. In the assignment, we need to analyze data collection and analysis to uncover patterns in vehicle speed reduction and recovery with a keen eye on road hump design. By dissecting these elements, the assignment aims to offer practical suggestions for optimizing road hump design to contributing to more effective traffic management and heightening road safety.
As can be seen in the figure, the site area is located at Lingkaran Ilmu, the road beside the football field of UTM. The road is a dual carriageway with curved geometry and flat terrain, and there are two junctions found along the road, which act as obstruction during the experiment process. Therefore, in order to overcome this problem, only the transport that pass through these two junctions are recorded. Our team conducted the digital method by using two radar guns. As can be seen from the figure, this is the work plan that we used to conduct our data collection. The first radar gun is used to measure the speed of the car before reaching the road hump and when the car reached the road hump. And the second radar gun is used to measure the speed of the car after passing through the road hump. The position of the radar gun is at an angle of 45 degrees from the roadside to the car aimed.
To get accurate data, we have followed the recommendation by Cover and Fold 2010 and collected 50 samples for the purpose of this study. As you can see in this pie chart, this is the breakdown of the percentage compositions of different type of vehicle involved in this study. We can see that the car leads at 74%, followed by motorcycle at 20%, bus at 4%, and lorry at 2%. In this study, we have also evaluated the characteristic of the road hump at our selected study area, and it is found that the road hump is considered as round top with the height of 80 mm, width of 4,200 mm, and length of 4,300 mm, which follow the guideline by the CRIM 2009, in which a road hump should have a height of 75 to 100 mm and width of 3,700 to 4,250 mm. As you can see in this slide, this is the frequency distribution for the vehicle speed at 30 meter approaching the road hump. It is found that 30% of the vehicles adhere to the posted speed limit within the campus area, which is 35 km per hour, and 26% of the vehicle drive between the 35 to 39 km per hour speed, and 6% of the vehicle were driven at a speed more than 50 km per hour. The S-curve showcases insightful findings on vehicle speed distributions. Analyzing the curve revealed that at 30 meter approaching the road hump, the 85th percentile speed was 44.2 km per hour, which indicate a significant portions of vehicle exceeding the speed limit. However, a significant drop to approximately 26.4 km per hour at the 85th percentile speed suggests that many drivers opted to reduce its speeds below the speed limit on the road hump. The descriptive statistic or speed data were presented in the table below. Approaching the hump, the mean speed is 38.34 km per hour with a 6.6 km per hour standard deviation, signifying a considerable speed variability. On the hump, there's a 38% reduction in mean speed to 23.76 km per hour, which reflecting a more uniform speed profile. Moving to 30 meter after the hump, there's an 18% speed increase to 28.98 km per hour with a standard deviations of 5.7 km per hour, which indicates that most vehicles speeding after the road hump.
Next, I will continue the presentation with the discussion. The main factor affecting road safety is speed. About 30% of incidents involve speed as a major contributing factor. By moving faster, it is more challenging to respond quickly enough to avoid an accident. Second, the injury is impacted by speed. When two objects collide at a faster impact speed, more energy is released that will cause more serious injury to the road user. Thus, various road facilities such as road humps are designed to control the speed of drivers, especially in residential areas and school areas. To design road humps, there are some considerations. The design and placement of road humps will affect vehicle speed recovery. First and foremost, the road hump's height, length, and shape are crucial. A well-designed road humps can reduce the shock to cars by allowing for a steady fall. This can help faster and more seamless recovery of speed after passing the road humps. Next, road humps should be positioned such that drivers can see them easily and have enough time to slow down. Moreover, the material used to construct the road humps is also an important factor to be considered in design road hump. Different materials are used to build road humps such as concrete, rubber, or asphalt. The material selection has an impact on upkeep, durability, and driver and passenger comfort levels. In a nutshell, road humps are essential for improving traffic control and road safety. Road humps, which are placed in residential areas, school zones, and regions where there is a lot of pedestrian traffic, successfully making the environment safer for both cars and pedestrians. Road humps greatly reduce the frequency and severity of accidents, particularly in locations where speeding is common. That's all from me. Thank you.
The main purpose of road hump optimization is to maintain the peak vertical acceleration of an oncoming vehicle at an acceptable level. Love et al. Investigated the effect of speed hump characteristics on vehicle speed and concluded that hump crossing speed increases as the speed hump length and spacing between humps increase, but decreases as speed hump height increases. Besides speed humps, other smart street designs such as roundabout can replace signalized and two-way stop control intersection, where the circulated flow produces fewer conflict points and lower vehicle speed. Next, a short yellow light display duration causes accidental red light running, while a long duration causes intentional red light running. Hence, the appropriate timing of yellow change intervals is important to reduce the occurrence of red light running, which leads to major accidents at signalized intersections. Locating medians and pedestrian crossing islands between opposing traffic lanes enables pedestrians to focus on crossing one direction of traffic at a time, reducing the risk of accident. Pedestrian walkways should be provided in urban areas with high pedestrian activities, especially near school and transit regions. Driver behaviors remain a huge cause of road accidents. Proper education programs should be introduced to monitor the driving skills and attitudes of adolescents on road to avoid careless driving and overspeeding. Compulsory rest periods should be introduced to prevent fatigue issues among long-distance drivers.
So we already in the last of our slide. So in summary, our examination of how vehicle speed recover after crossing road hump highlights the importance of careful design for effective traffic management and increased road safety. The results emphasize the need to precise road hump planning, considering factors like vehicle type and traffic flow. So, recognizing road hump as a vital component in urban setting, we can propose practical modification to enhance their effectiveness through optimizing road Hump design, we aim to contribute to a more straightforward and efficient traffic management system, creating safer roads for everyone involved. Thank you.